Good morning, good evening, good afternoon, whatever the case may be. We are back and better than ever, and we certainly are going to stir it up today because we are talking about optimization, and we are going to use some calculus to optimize some things or to find some maximums and minimums, which I think you would agree is quite important. We can actually do it using graphing. If it's a parabola, we could use the formula to find the x-coordinate of the vertex of a parabola, or differentiation, which we've already been doing, to find the max and mins of functions that model the particular situation. We do need to be careful because the max and mins might not always occur where our first derivative is equal to 0, where we have a turning point. Because the function could have an endpoint that's greater than a local maximum, as is the case here. And if our domain is only from A to B, as shown here, then this would be the maximum across the function. But if this continued forever and ever, then we would use this, depending on the domain. It depends on the problem. And here, the local minimum is also the absolute minimum, the lowest point on the graph here, compared to this. Ways we will do that: we can use sign diagrams after taking the first derivative. We can use a second derivative test if we want to, and of course we could do it by graphing. But let's jump right in, shall we? We have a rectangular cake dish. You like the cake? Love the cake. I love the cake. And it's made by cutting out squares from the corners of a 25 centimeter by 40 centimeter rectangle of tin plate. So it's a soft metal, and the original piece of tin is a full rectangle. But what happened is they cut out these 4 little blue squares and then folded up the tabs, folded up this and this and this and this to form this cake pan. And what they want to know is what size squares should I cut out so we have the maximum amount of volume. Okay, and so we don't have any sort of function here. We're going to have to come up with our own function. And how do you do that? Well, you look and see what we're being asked to find the maximum or minimum of. In this case, a maximum. And that is what we're trying to find here is the maximum volume. Well, the volume of what? Well, this is a rectangular prism, and we know that the volume of a rectangular prism is given by length times width times height. Okay. Problem is, we don't have anything for length, width, and height of this thing. But what we do know is that from here all the way to here is 40 centimeters, right here. 40 centimeters. And we know that from here all the way to here is 25 centimeters. Okay, so we know that much. And then we say, what size squares must be cut out? Well, why don't we let the sides of the squares be x? So this is an x, this is an x, all the same size squares. This is an x, this is an x. And we know that all the sides of a square are all the same size. So this is x, this is x, this is x, this is x. I just don't want to label it because it'll get too junky looking. Okay. So let's think about this now. If from here to here is 40 centimeters, then from here to here is 40 centimeters. And if this is x, this is most certainly x. And if this is x, this is most certainly x, because we have a rectangle, or these are squares, all the sides are equal. So that helps us get the length of the little tab here that's folded up to be this side. The length of this tab is 40, the entire length, minus the 2 x's. So this would be 40 minus 2x. By the same reasoning, this length right here, from here to here is 25, and each of these little guys is x as well because this is a square. All the sides are equal to x. So from here to here, that length is going to be 25 minus 2x. So now I have the length of my rectangular prism. So it's 40 minus 2x, and I have my width right here. It's 25 minus 2x. Okay. Well, what's this height? Well, think about it. If this length right here is x, and I fold up this tab, it's going to be x centimeters height. So I have my length, I have my width, and I have my height, which I can replace in this wonderful formula. And I would have 40 minus 2x multiplied by 25 minus 2x multiplied by x. And now we have a function of which we can take the derivative of and try and find a maximum point, or the value for which the value of x for which the volume is maximized. And that value of x represents the length of the sides of the squares. I'll save you a little bit of trouble, and I will expand this for you and tell you that it is equal to 1000x minus 130x squared plus 4x cubed. And again, that's if you do the algebra here and expand and multiply through by x. So now we're ready to take the derivative to help us find the maximum. So the derivative of that would be, let's see, 1000 minus 260x plus 12x squared. And how do we find the maximum of a function? We take its derivative and we set it equal to 0 to try and find a turning point. Okay, so I'm going to rewrite this as 12x squared minus 260x plus 1000, and I'm going to set that equal to 0. Okay, I can factor out a 4, and I get 3x squared minus 65x plus 250, and that's equal to 0. So now I need to factor this, so that's going to be 3x, or you can use the quadratic formula, 3x times x, and the factors of 250 are pretty simple, minus 5, and let's do minus 50. Okay, you'd have to figure that out again, or use the quadratic formula. So solving here, we would have x equal to 50/3. Or x is equal to 5. Now that satisfies this equation right here. But we need to make sure and see if these answers are even possible. So this side right here is a length of 25, and if I cut out 5 centimeter squares from either side, I'm still going to have 15 left, and I'm going to still have 30 left here. 50/3 is equal to 16 2/3. Okay. But let's forget about the 2/3 for a second because it's a little more difficult to work with. Let's just think about 16. If I cut 16 centimeters this way, I would not have enough to cut 16 centimeters the other way on the other side, because 25 minus 16 is 9. I'd only have 9 centimeters left. So therefore, this is not even possible. So our only possibility is x equal to 5. And we think that we should cut out squares of length 5 centimeters, of sides of length 5 centimeters, to maximize the volume of our rectangular prism. So how can I figure that out? Well, I can use a sign diagram where 5 is my 0 of my derivative. And I can use the first derivative test. And I'm going to choose, I guess I'll choose 0 to the left of 5. Replace x with 0 in the easiest function that I have. Maybe it looks like it's this one. 0 minus 0 plus 1000, that is going to be positive. And then I'll try 6. This here looks a little bit more friendly for 6. 3 times 6 is 18, minus 50 is a negative. 6 times 5, or 6 minus 5 is 1, that's a positive. And this is a positive. 4 is a positive. So a positive times a negative times a positive is indeed a negative. And clearly, I have a local max or max at x equal to 5. So the answer would be, let's see, these squares, something like this. The squares should be 5 centimeters by 5 centimeters to maximize the volume. Okay, so there we did it using calculus. Okay, but let's take a look at what it would look like graphically. Let's graph the volume formula and see if the maximum does indeed occur at x equal to 5. Well, I've already graphed it, as you probably have guessed, and I just rewrote the function here. But if you look, I found the maximum. It occurred when x equals 5, and then this is the function for the volume. So at x equals 5, the volume will be 2,250 cubic centimeters. And you might think, hey, well, what about up here? It's going up and up and up and up, where the volume really is going to increase. Well, yes, but remember, we only have so much square we can cut out before we run out of material on the tin plate. And if you go to here and go straight down, you can see it's 20-something. I mean, x would have to be equal to 20-something to get a value greater than 2250. And there's just not enough material to cut out squares 20-something centimeters in length. Okay, that is all I have. I will check back in with you tomorrow. Not tomorrow, the next video. See ya!